Hi, everybody. First, to start with a bit of a personal note, that I'm really delighted that what we've been fantasizing like maybe 5 years ago back in Montreal has really come to fruition, and that everybody from Jülich and Montreal and Zagreb are here in Zadar today. So really fantastic that this could happen. So today I'll talk about this neuron-centric view on segmentation of cortical layers in, of course, human brain, and we developed this approach with explainability in mind. So let me start. So we heard really a lot fantastic ideas and approaches, and also results regarding the big brain and quantitative histology, and really fascinating stuff. But what's kind of underlying all the discussions and debates around this is that the parcellations and definitions are very, very elusive, right? So for instance, here we have a picture that we've seen a lot of times this in the past few days, and that's that there are obviously layers in this cortex, but it's really not that easy to really pinpoint to draw this line, as I will show later. So now we have all this data and technology available to really, for the first time, zoom in on the details that the giants were maybe a century ago or even more observing under microscope and drawing by hand, and then we still have this their drawings today on our slides. So it's still the basis of this functional neuroanatomy. So we developed machine learning pipeline. So a classical machine learning pipeline that as an input takes a histological slide. The first step is to identify, localize, and segment all the neurons in the slide, and then develop features that I will tell about today to be inputs in a classical machine learning segmentation task. So just a bit of detail about dataset. Those are sections from Zagreb brain collection, scanned in-house at high magnification, and it's at the sub-micron level resolution. So I think all these things could work at 1 micron level as well. So this was developed during my visit at the MNI and my work at Croatian Institute for Brain Research. So taking another look at the dataset, this is how this stuff looks like. Some sections were a bit thinly sliced, some were a bit thicker. So just to give you a sense about the data. So the first thing is that we focused our research not on a pixel-based but neuron-based view on histology, right? So it all starts with neuron, and we're focused on the neurons themselves in this research. So the first thing was to really pinpoint the location of each neuron, then segment them out and create vector representation of neurons. So you could say this is something like neuron to vec, if you're familiar with this embeddings and representations. So when you have this vector representation of neurons, then it's no longer this unstructured data, but you have this structured data of all the neurons in the slice. And then you can apply various machine learning and data science things to get your results. So I spoke with Eric and Sebastian yesterday, and so really the focus here is it starts with good and as precise as possible neuronal segmentation. And this is the thing I wanted to show you yesterday, that we first smoothed the image by this anisotropic peronomalek, it's called the technique. So the signal becomes much more smooth and less noisy. And then it's much easier to segment out neurons. This is Nguyen neuronal staining, if I missed to say this. So only neurons are visible. And after precise location, it's easy just using a watershed, which also facilitates this smoothing also facilitates the watershed process. Let me just stand up a little bit. So you get these things even more easy. And this is the one example of output. I'm not sure if you see it well. Here, larger neurons are shown brighter, right? So you see that this is the layer 3 with big pyramidal neurons, and maybe this is layer 4 with many smaller, densely packed neurons. So recently, we were working on advancing our neuron segmentation, with one of the ideas being that the recent Sartorius cell instance segmentation on Kaggle had the same task that people compete against each other on. So the average precision metric was about 0.35, so which is not the best. And the winners made a crazy ensemble of different deep learning methodologies, and this is their results, right? So we just tried, okay, maybe we can, this is not working, but never mind. We can just maybe take their results and see how it works. But turns out it didn't work that well, because the images that they were training on were different than the ones that we have. So what the next thing we are trying to do, I hoped it would be finished for Zadar, but it was not eventually, is to use the same approach. And in the meantime, Facebook published a new detector on 2 neural network that was trained on common objects dataset. So it's not originally trained on the balloon classes, but there is an example, and it's really, really simple to retrain it on balloon dataset, and it works really well, like shown here. So of course we will do it on neurons dataset, because we have a lot of these masks from our previous research, right? So that's one thing to do, and it's kind of a weak supervision, right? So you don't really have exact segmentations that you need really very many for these deep learning systems to work. And so we'll see how this turns out. This also allows us to detect this tissue problems like this folding, and we can also very easily eliminate those from the training set. Or we can also add them later, so the model can learn this as well. There's also interesting concept, noisy student, where you have this a large network that then you distill and have a smaller network that's a student, and then the student then feeds its results back to another large network. This is maybe something Professor Kostovic and I can talk later in regard with dropout and regularization. So the main thing is, as I said, this characterization of neurons. Once you have these neurons segmented, you can do stuff like area, gray value statistics, circularity, perimeter, and stuff like that. And really plotting only these on our slide, really you see the some kind of properties emerging based on, let's say, only neuron size. Really nice layer 2 and layer 4. Even better here for neuron density. So how many neighbors in, let's say, 300 microns area, or average neighborhood size. So it's important to say that not only we have statistics of individual neurons, but also their neighborhoods, like 50, 10, 100, 500 nearest neurons. So what's going on around one neuron is what we are interested in. So many measures were developed. We even looked at this convex hull of a neuron. So what are the properties of neuron hull? Is it is it elongated? Is it circular? That also helped us in some ways. I'll show you how. Like for instance, here, it's very easy to segment the layer 1, or to better say, detect layer 1 and white matter neurons, because of course, these white matter neurons have very large sparse area around them, but layer 1 neurons are packed between like the outside of the slide and layer 2 neurons. So it's super easy to develop cortical depth as a feature of each neuron, and even cortical thickness around the whole slide. And just a bit of a spoiler, we put this in the machine learning pipeline, and this feature was overwhelmingly more important than anything else. And it produced super smooth, perfect parcellations of the cortex. But it was not as accurate, and it's also not that informative. Okay, we have cortical depth, but we don't want to know the information on such a huge scale. We are interested in saying this neuron is layer 3 neuron because of exactly this, his local property. Its local property, or the property of some small neighboring area. So putting all these features in projections or embeddings really revealed that there is a structure the structure can be captured during these handcrafted ad hoc features. Of course, there's room to develop more features, but I'm showing what we have right now. So this was PCA, this was TSNE, and this is UMAP for each of 3 raters. So we have, what's important to say, that we have 3 different raters who labeled this part of the, let me show you, this part of the section was labeled by 3 raters, 2 from Croatia and 1 from the MNI. So as we all know, it's really hard to create precise delineations. I mean, just look at this. Look at this difference. Let's say, why is this not working? Between the 3rd one and the 1st one, or the 2nd one. So you can say, how can you even learn something that you don't know what you're after? Of course, we are also after the unsupervised approach. I'll talk about this just a moment later. But okay, we tried. Let's see what we can do with this. So we turned to tree-based models, as we didn't have that many examples for neural networks, and we wanted to stick as much as possible to the models that are understandable and efficient on this small data. So it's also nice to say that okay, just before that, that they are ensembles. So I will in just a moment say a bit more about that. So this is when we wanted to learn just the 2nd and 4th layer. So from the 2nd rater, the model generalized really well. Like from the 3rd rater, it was not that good. From the 1st rater, so. So it's also interesting to see how the model is able to replicate the humans, right? So in ensemble learning, weak classifiers are combined to achieve better performance. And there are 3 main reasons for that. The first one is statistical, which stems from the fact that data is often too small in compared to the search space. Like, so it's by combining more different smaller data or weak classifiers, we lowered the possibility of choosing the wrong solution. Right? The second one is computational, and it's with regard with model selection or initialization. Like, where do we start from, and which model do we choose, like the input parameters and so on. Also, combining those kind of removes the possibility of choosing the wrong final hypothesis. And the final one is representational. Maybe the solution is not even in the search space of the model. So this extends the search space that the model can converge to. And in regard with brain segmentation, so I think we can apply the same reasons for using ensemble learning, because of course we have low number of images. So just try different models on the same small number of images, and they can give you different results, which then you can combine and again remove or lower the possibility of going totally astray. And in computational reason is that, like, previous experiences of raters are something like initialization of the models, because every person will delineate differently. So by combining those, we also remove the possibility that you are biased towards a single rater. Right? And representational, as I said, no one really knows where the boundary is. So maybe no single person can give us accurate delineations. And by combining three different raters or combining their knowledge, we can even extend the search space in this matter. So in the end, we got this. So I think it's fairly nice generalization across all layers. So this is the input data for this particular section, and I think the model really generalized well. Right? So what we also have here is the model interpretation. Using, perhaps you're familiar with the SHAP approach and the Shapley values. It's from the from game theory, how much each participant helps in finding a solution in optimization problem. We can say, for instance, for layer 6 neuron, for this particular neuron, this and this feature contributed mostly for this neuron to be classified, as a layer 6 neuron, or which of these features helped as not being classified as layer 2 neuron, for instance. So we can do this for at the instance level, or we can do this also at the model level, of course, which characterizations, which features in the neuronal representations are most informative for a given model, right? And okay, getting short in time, so I'll just skip to also what Goran proposed. He said, Andrija, can you, if this would not be a layer 3 model, neuron, what would it be? What would the model say if it didn't classify it as, let's say, layer 3 neuron? So we can ask in this framework, we can ask such questions like, what if, right? And you can see also that there is a emerging structure of this what if. So in layer 3, there is a consistent 3 or 4 sublayers different for this what if questions. Okay, these are layer 3 neurons because that's what was in the input parameters. That's what we learned from raters. But we also can observe here the emerging of this sublayering structure. So with this framework, we can also ask questions such like this, right? And maybe discover also that there are not maybe 6 layers across the cortex, or maybe sometimes more, sometimes less. and also establish which exactly properties of neurons led to that conclusion. Just a short remark about deployment. We were looking into using the TensorFlow or TensorFlow Extended, which is a set of components that implement this end-to-end machine learning pipeline that helps you with data provenance, quality and experiment tracking, and also scaling and development. But with all fantastic tools presented here, I guess we can work something out, maybe to combine these two or just use the other stuff, right? So to summarize, this research aims for this data-driven, bias-free. When I say bias-free, I mean no human in the loop, no learned old knowledge, no dogmas imposed in this in cortical parcellation, right? And we can only achieve this by trusting the model. So that the model can be interpreted, that I can say, okay, the model learned this because of this particular reason. Yeah, so we need to trust the models we are using this. And I guess maybe for the first time, we'll be able to, by combining this massive data sets at higher resolution and interpretable machine learning and all the wonderful stuff we presented here, we can maybe redefine and discover new things in this century-old beliefs and really help advance neuroscience and this fundamental level. Thank you very much.